Welcome. In this lecture, we are going to be looking at how dynamic polymorphism is implemented. But before that, I want to take a little foray into understanding how our machines actually work just a little tiny bit better. Now, this isn't going to be a massive in-depth look into assembler, but it is going to be a tiny little skim of assembler. So let's go to a website called godbolt.org. Great little website if you ever want to look at what little chunks of C++ are actually doing. Here's an example I was working on a little bit earlier. We don't want that one just yet, but you can see the idea is that you write code on the left, and on the right you get to see the assembler that's going to be, is basically one step away from the binary that gets actually run on your machine. So I'm going to copy over this code into our godbolt.org. You can see it's compiling over on the right to create the assembler. And you can see it's color-coded the lines. What it's doing here is each line that's been color-coded basically corresponds to a bunch of lines over on the right. So one line isn't necessarily one instruction on a CPU. It could be very many instructions indeed. So what happens is that we can take a little look at this. For example, if I right-click, I can scroll to the assembly, and you can see that this gray chunk here that's highlighted when I have my mouse over it, all of that is this line here, printing I'm an animal. Okay, so we don't need to worry about all of this. What I want you to look at is how this is structured. Look at how it's laid out. A function over here is a function sort of over here as well. These functions are actually called labels in assembler because they are just memory addresses where those instructions are in memory. So for example, cat : cat is defined by this list of instructions. Main is defined by this list of instructions, and so on. So that's basically how it works. So how does a function usually get called when we don't have all this virtual stuff, when we've just got static polymorphism? I'm going to remove the virtual keywords so that we can just take a quick little look at that. I'm going to remove virtual, I'm going to remove override because it's going to have a little moan about that, and see what we come up with. I want to particularly take a look at these lines where we are calling make noise. Let's scroll to the assembly and take a look at that. There is one instruction called call, which is basically for calling a function, and it's calling the animal : make noise. What is animal : make noise when it's turned into binary? Call is clearly just a set of binary instructions that tells the CPU to do something, but what is this? Well, if I go up to the left of this pane, you can see there's a compile to binary and disassemble the output. No, that's the wrong kind of hover thing, but there's this 1100 kind of thing. If I click that, what it's going to show us is the actual addresses involved here. So down the left, what we have is, well, we've actually got binary as well, but down the left, we've got the address in memory of this instruction once the assembler binary has been written out. And if I scroll to this make noise again by right-clicking, going to scroll to assembly, that didn't quite do the trick. Here we are, got the call, and you can see that this is just calling to a number. If we go and look at that number in memory, so it's 480, 850, where's 400, 850, you'll see that it's the beginning of the animal make noise function. So when we've got an instruction to call a function with static polymorphism, it's literally hard coding the address of that function into your binary. So it's really, really efficient. It's super efficient. It takes one instruction to make that instruction call. So that's why C++ does it by default. That's why we use static polymorphism by default, because it's really cheap. And you don't need the dynamic polymorphism half the time, so why not do the cheap thing most of the time? That's what C++ is saying. Always doing the efficient thing when it can. But what if you don't want that? What if you don't want the static polymorphism? How is that actually implemented? Well, let's take a look. I've got a slide deck here for you talking about it. It's implemented with a function known as vtables. So let's take a look. We've got this array of animals. So it's an array of pointers to animal objects. But remember that the compiler doesn't know what type of animal objects they are at this stage, it just knows that they are animal objects. So that's all it can treat them like. However, What if this animal object had a pointer to something else that we're going to call a vtable that's specific to the exact type of animal that it is? That is how we can tell what function to call. So for example, if the vtable pointed to by this first animal object is the cat vtable, then we know it is a cat. But more specifically, what does it actually mean to be a cat? Well, it means that you have cat-like functions. And that's exactly what a vtable is. It's a virtual method table, hence the V, hence the virtual in C++. So the virtual method table is just a list of pointers to the function implementations. So what we have to do when we call .makeNoise on the animal is say, okay, animal, give me a pointer to your vtable. Okay, vtable, give me a pointer to make noise, and then we'll call that pointer. Same thing happens for a dog. You point to a different vtable, a dog vtable, and you would make noise. Now, what if you had a second cat in your array? Well, you're not going to have a second vtable for cats as a whole. You just point to the cat vtable because that's going to point to the right implementation of make noise. Very simple. That is how how vtables work, how this dynamic polymorphism is actually implemented. Okay, so with that in mind, let's see how this call changes and how a few things change when we go ahead and hit virtual in. In fact, I'm going to leave that as a challenge for you. You go and put virtual back in, put it into Godbolt, have a little play around, and see if you can figure out what it's doing. Now, don't worry if you can't figure out what it's doing or it just completely perplexes you, because this is assembler and I don't expect you to know anything about this, but it's just interesting to see whether this changes, whether it's still a static address here or not. Pause video and have a go. Okay, welcome back. So I'm going to stick virtual in. Actually, you don't need the override to make this work. Virtual on its own is going to be enough to add the behavior that we're looking for. So I'm going to go to 34, scroll to the assembler, and suddenly that really simple call that we had has become far less simple. It's actually saying now, call the thing pointed to by the register RAX. That's what that means. Don't worry if you can't decipher assembler. I really don't expect you to be able to decipher assembler. But what you would have noticed is that it's no longer that fixed address anymore. It's been populated by this process that I was mentioning, this vtable process. And if you've been really astute, you might actually notice that at the bottom of the assembler, maybe not at the bottom, but somewhere in the assembler, near the top in this case, you've actually got the vtables. These things here are vtables. Now, how can I tell that? That's weird that I can tell that. Well, if I switch off the binary, it will be far clearer. And in fact, it goes and puts it at the bottom because it's no longer laid out like it would be in memory. And you can see this section at the bottom. So disable 001, you can see this section at the bottom, and it says vtable for cat, and it tells us how the vtable is laid out. It has a pointer to make noise. We've got the vtable for dog here somewhere as well. It's got a pointer to dog make noise. And the vtable for animal has a pointer to animal make noise. So these are the tables that are being pointed to. They're actually fixed in program memory, just like the functions are. You can't change them at runtime. So, but they are being pointed to by animal objects. So that is how the animal objects know where to go. And there's the whole process of looking it up, which is as we described. If I have been given an animal pointer and I want to call make noise on it, I say, what's your vtable? Okay, and then let's look up make noise in your vtable. And okay, it's cat make noise. I'll go to the address of cat make noise and execute that function. So that's how vtables work, very simply, and you can even see it happening right there in the instructions, a little bonus for you. Okay, I hope you've enjoyed your introduction to vtables and polymorphism. If you like this stuff, let me know in the Q&A. If you don't like this stuff, then also let me know in the Q&A. If you're like, Sam, this is totally confusing, please take it out, then do let me know that in the Q&A. And we'll see you in a few lectures' time from my part.